Our lesson today is on arithmetic sequences. We're starting a new section, and I am going to start out with this basic sequence right here. So let's look at the following sequence of numbers. We have 3, 8, 13, 18, 23, and it continues to go on and on. That's why you see this dot, dot, dot. That means that sequence continues to go on. So we will say the dot, dot, dot at the end means that this sequence goes on forever. Three, 8, 13, 18, and 23 are the actual terms of this sequence. So each one of those is called a term. There are 5 terms in this sequence so far. 3 is the first term. 8 is the second term. 13 is the third term. 18 is the fourth term. And 23 is the 5th term. So there's nothing fancy about that. We're just counting in order. This is an example of an arithmetic sequence. Now I know it looks like arithmetic, and I believe it's spelled the same, but it's called arithmetic when we're looking at these sequences of numbers. This is a sequence where each term is the sum of the previous term and a common difference. So this common difference that we call D here is important. So if we were to look at, I'm just going to go right back up here. Okay, here's our first term, our second term, our third term, fourth term, 5th term, and it continues to go on. If I look from my 3 to my 8 and my 8 to my 13, we have a common difference. We are adding something here. In this case, we are adding 5 each time. So the common difference here would be 5. All right, so we've got a table over here just to kind of take a look at some things and see kind of what different things represent. You're going to see this right here, these A's with these little numbers. The way you read that is you say A sub 1 and A sub 2 and A sub 3. That means the first term, the second term, the third term, the fourth term. So see our first term, we can write it as A sub 1, and that value is actually 3. Then we have our second term, A sub 2 is actually 8, and so forth. So we could finish this. We know that our fourth term, A sub 4, is 18, and if we want to, we can just look back at this previous term, which was 13. We know that we're adding 5, so we get 18. And then our 5th term, add 5 more, and you get 23. And then you can keep going. So basically, we know that we're adding 5 to our previous term. So if we were to look at this right here, this is our term number, okay, and so because it goes on and on and on, if we were to say that n represents any term number, and then a sub n is just representing a term number, if we wanted to find out what it would be, we would have to look at the previous term and then add 5. So this would be written as a sub n minus 1, meaning the term you're looking at minus 1 to give you the previous term, plus 5. If we were to write it in function notation over here, the first term they have written as f of 1 is a formula to find the first term, and then f of 2 would be the formula to find the second term. F of 3 would help us find the third term. F of 4 would help us find the fourth term. F of 5 would help us find the 5th term. And then all the way at the bottom, f of n would help us find the nth term. How can we find the 9th term of this sequence? So we've found up to the 5th term. If we wanted to find the 9th term, we could just keep adding that common difference of 5 until we get to the 9th term. So we can say keep adding the common difference until we reach the 9th term. Okay. One way is to start by finding the previous term. So if we take a look at this table, we have and this is just kind of breaking down what we were doing. We have our 3rd term, and then we know that we were adding 5 each time. So 3 plus 5 gives us that 8. And then we take 8 and we add 5 again, and that gives us our 13. And then we take 13 and add 5, and that gives us our 18. And so see, we keep bringing down the previous term. 18 plus 5 is 23. So we can keep doing that. We can say, okay, well, 23 plus 5, which would be 28. And then we could go 28 plus 5. 28 plus 5 would be 33. 33 plus 5 is 38. 38 plus 5 is 43. And that is our 9th term. So we could keep doing that. You can see over on the right hand side the function notation that's happening there. Write a general equation that we could use to find any term in the sequence. So if we're trying to find a term in the sequence, we would write a sub n equals, and then we would have to know the previous number. So we would have to know a sub n but minus 1. See, because here, look here, a sub 9, in order to find a sub 9 was 43, we needed to know a sub 8, right? We needed to know this. So a sub 9 minus 1 would be a sub 8, which would be this one, and we would add 5 each time. So the way we write that is we say a sub n minus 1, and then we would have plus 5, because we would have that out to the side. This is called the recursive formula. In order to solve for a term, you have to know the value of the preceding term. So in order to know the 10th term, we needed to know the 9th term, the one before it, so we could add 5 each time. Can you think of a situation where the recursive formula would take a really long time to use? Well, what if I wanted to find the 100th term? That means in this case, I would take my 9th term, which is 43, and I'd have to add 5 for the 10th term, then 5 to get the 11th term, and I'd have to do that all the way to 100, and that would take a really long time, but that would be an example. So we could say, if I want to find the 100th term, so here we're going to look at another way to find some unknown terms. Now this is still the same sequence, okay? We're just going to point out what's going on here. So we've got our first term was 3, and then we know that we were adding 5, and that gave us 8. And then we had 8, and we added 5, and that gave us 13. But notice this. Notice that this 8 here is 3 plus 5, right? It was really this that came down to here, and then we just added 5 more. See? And then if we were to take the this 3 plus 5 plus 5 right here, and then we added 5, and then we take that and add 5 each time. It's just another way to look at it. If we want to look all the way down here and finish filling in this function notation, we're down at term 8. We could say that we could find that by taking, oh, and I probably should have gone over here to the side, sorry. So basically, we take our first term, and notice that this one is just 3 plus 5, which is the same thing as 3 plus 5 times 1. And then the next one is 3 plus 5 plus 5, which is 5 times 2. See, there's 2 of them. and 3 plus, and then there's 3 5s, and then 3 plus, and then there's 4 5s. And notice that pattern keeps going. So then when we get down to here, we're going to have 7 of those 5s, okay, because it's the 8th term. Now you might be saying, well, what's this a sub 1? That is our 3 here, okay? That's the 3 that can kind of keep carrying down. And so then we end up down here with a sub 1 plus 5 times 8. And so write a general equation that we could use to find any term in the sequence. Well, in order to do that, we would write a sub n is equal to, now that 3 was what stayed constant all the way down. That is my first term. The way we write first term is we write a sub 1. And then we were adding 5 each time. And now look what you had here in parentheses. See, here we had 8. Well, that was 1 less than my term number. Look up here because these are kind of over top of the chart here. 4 is one less than my term number. So the way we are going to write 1 less than the term number is we're going to write n minus 1. And this is the explicit formula. This is really, really important. To solve for a term, you need to know the first term of the sequence. Okay, that would be right here. This represents the first term. And the difference by which the sequence is increasing or decreasing. And so this number right here is your common difference. And while this may seem overwhelming, once you get the hang of it, it's really not going to be that bad. You'll be able to breeze right through this. Okay, consider the sequence 10, 4, negative 2, negative 8, and of course we've got the dot, dot, dot. It continues on. Write a recursive formula. Now remember, the recursive formula was the formula we used when we needed to know the previous term number in order to get to that. So I want you to box this in, and I'm just going to show you this one, and I want you to know that the recursive formula is going to have 2 parts. Write yourself a little note. There's going to be 2 parts. Okay, so the first part is that you're going to write a sub 1 equals, and you're going to tell me the first term, which is 10. See, there's the first term. Okay, that's the first part. The second part you're going to write is you're going to write a sub n equals, and then remember with the recursive formula, we needed to know the number before to help us figure out the next number. So we would write a sub n minus 1, and then look and see what's happening here. So to get from 10 to 4, we're subtracting 6. So with arithmetic sequences, we're either going to be adding or it's going to look like we're subtracting. So if we look, we keep minusing 6, right? Okay, so this is going to be a sub n minus 1, and then it can be written as plus negative 6, or, and I'm just going to do this in a different color because it's not a third step, or you could have written a sub n minus 1 minus 6. So you've got to have the previous number, and then once you know that number, you can add negative 6. See, in order to get to 4, we needed to know that this was 10 so that we could subtract 6. In order to get negative 2, we needed to be able to know this number was 4 so that we could add negative 6 or subtract 6 and get to this. All right, so the recursive formula, it has 2 parts. And I don't want you to think that green part is like a third part. You only need these 2 parts. All right, an explicit formula. Write an explicit formula for the sequence. So the explicit formula, it's always going to look like this. A sub n equals, you're going to start out with the first term. What is the first term of this sequence? It is 10. And then we're always going to look at what we're doing. We're adding or subtracting. Looks like we're subtracting 6, so we're going to write minus 6, and then you always put n minus 1 in parentheses. And that's it. You're done. Okay, so with this one, the explicit formula, you take the first number, it goes here, and then look, are you adding or subtracting? If you're adding, you're going to have plus that number. If you're subtracting, it's going to be minus that number, and then multiplied to n minus 1 every single time. So this one is actually very helpful because this next part asks us to find the 42nd term. Well, I know that I'm starting with 10 and I'm subtracting 6 each time, but I don't want to sit here and have to keep going minus 6, write that number down. Minus 6, write that number down. Minus 6, write that number down. That's going to take a while. That's pretty much what this recursive formula has you doing, okay? The explicit formula is awesome because you can take that and you can plug your 42 in there for n, and you will have your answer. So we're going to write a sub 42. Now that there's nothing to actually do there. That just says I'm going to evaluate this formula when n is 42. That's all it means. So then I have 10 minus 6 times, oh, there's my n. I'm going to put in 42 minus 1. So now I have 10 minus 6 times 41. 10, and then that's going to be minus, that ends up being 246. And when you subtract that, you get a negative 236. And so you can say a sub 42 equals negative 236. What that means is if you had subtracted 6 until you got to the 42nd term, it would be negative 236. All right, I would love for you to pause this and try this one and just see how far you can get using the previous example, and then start this back up. All right, so consider this sequence that's given to us here. We've got 7, 17, 27, 37. If it were me, I would look at that and say, okay, I'm adding 10 each time. All right, that's my common difference. And maybe you make a little note that D is 10. That's your common difference. Find the next 3 terms of the sequence. Well, that's pretty easy. So we would have 47, 57, and 67. Those would be the next 3 terms. Write a recursive formula. Remember, a recursive formula has 2 parts. The first part is a sub 1 and whatever the first term is, which is 7. The next part is a sub n equals, and then we always put a sub n minus 1, which means we have to have the previous number, and then we're adding 10 to get to the next number. So then we put plus 10. Part C, write an explicit formula. Okay, well that's the one that's super helpful, and it looks like this. A sub n equals, we put our first term, which is 7. We look at our common difference. Okay, we were adding 10 each time, so we say plus 10 times n minus 1. Find the 33rd term of the sequence. So we're going to use that explicit formula, and we're going to plug in 33 for our n. And you should get 327. So a sub 33 equals 327. Alrighty, very good. Hopefully you're following along okay. Let's look at this beat the test. Johanna is conditioning all summer to prepare for her high school's varsity soccer team tryouts. She is incorporating walking planks into her daily training plan. Every day, she will complete 4 more walking planks than the day before. Part A. Johanna starts with 5 walking planks on the first day. Write an explicit formula that can be used to find the number of walking planks she completes on any given day. So we know she starts out walking 5 planks. Then it says she's going to complete 4 more than the day before. So if we were to figure out 4 more than 5, that would be 9 on the next day. 4 more would be 13. 4 more would be 17, ... So I like to start out by just writing the numbers out, looking at my sequence here. Okay, because they tell us to write an explicit formula, we have to start out and we say, okay, a sub n equals my first term, which is 5, plus, what am I adding each time? 4, and then n minus 1. And that's it. That's your explicit formula. You're done. How many walking planks will Johanna do on the 12th day? All right, well, let's use that formula we came up with. A sub 12 equals 5 plus 4 times 12 minus 1, which is 5 plus 4 times 11, 5 plus 44, which is going to be 49. So A sub 12 equals 49, which is answer choice A. All right, and there's one more on the back here. The following figures were created with squares where each side of the square has a length of exactly 1 unit. A sub 1 represents the area of the first figure. A sub 2 represents the area of the second figure, and so on. Based on this pattern, what would be the rule for the area of the nth figure when n is greater than 1? All right, well, you can go ahead and see that this is our fourth figure, so A sub 4 is our fourth figure. N is 4, that just means our fourth term here. I think if you look here, 1, 4, 7, can you see what you're adding each time? So what should be over here? Looks like you're adding 3, so this should be 10. But we are supposed to be looking at, oh, look here. Do you see these n minus 1s? That means they have written a recursive formula. Now, remember I said that has two parts. A sub 1, the first term is 1, right here. And then A sub n was equal to A sub n minus 1. And then what are you doing each time? You're adding 3. Now, they do not have that first part that tells your first term listed on here, but hopefully you can see that, whoops, I messed that up. Answer choice C would be the correct one that matches this choice. All right, I think that is the end of that lesson. Hopefully you followed okay through there, paying attention to the recursive formula and the explicit formula. It should go pretty well. If you have questions, let me know.